Okay, so we're going to look at the an algorithm was designed. We're going to look at question 28. So an algorithm was designed to remove repeating consecutive characters in a phrase, replacing them with a single character. The algorithm allows input of a phrase, removes repeated characters, displays the shortened phrase. So for example, if the input is that, the output will be that. Note the function write mn gets the last n characters of n. There are errors in the algorithm. Here's the algorithm. Perform a desk check on the algorithm using dd triple dj. Okay, so all right. So first things first, triple d g, I should say. So how we do a desk check is you want to the way to do this is you want to basically just write out all the write a table and write out all the variables. So you have phrase, you have len, you have new phrase. What else? New phrase, new phrase. You have done. And then you have output, right? So that's basically so you want to write those out basically, and so you divide it into like columns like so. So the phrase is obviously going to be d d d y. So you write your table, you write our variables, and then what's going to happen next is you're going to go down each line, and you're basically going to figure out what happens. So you've got the input phrase, phrase equals phrase plus x. So the phrase is going to be now obviously d, 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 y, x. So len equals number of characters in phrase. So the len would in this case be 5. Actually, I'm going to write the 5 down here because when you write the 5 down there, you want it to be aligned with whatever step you're at. You don't have to, but it just looks neater and it's easier for the marker to understand. Repeat, done equals false. So I'm just going to write F for false there. New phrase. So new phrase also equals nothing. So I'm just going to write empty quotes there just to say it's nothing. New phrase equals new phrase plus first character of phrase. So basically that means first character of phrase. So see how they like, so one thing with pseudocode, which you have to be aware of, is that they don't actually just say like, they don't access a string as you normally would, like get the 0th character, like get phrase 0, which would be like the first character. They just say first character of phrase. So in this case, it would be D. So it becomes D. I repeat, if first character of phrase does not equal second character of phrase, first character of phrase does not equal second character of phrase, then done equals true, which is false because D equals D. So that's the comparison. So you'd say D equals D. Len equals len minus 1. So now len is 4. Phrase equals write phrase len. Gets the last n characters of m. So phrase becomes the last 4 characters. So it'll become D, D, Y, X. Let me rewrite this. D, D, Y, X. So basically, you just grab the right 4. Okay, so then we say, is done equal true? No, done is false. So we repeat. If first character does not equal second character, done equals true, so it's not done. Then when you say len equals len minus 1, which is 3, so then obviously this will become D, you'd get rid of, it'd be dyx. Dyx, and then you would say, so len is 3, dyx, len is 3, and then you'd say the new phrase, well, you don't change the new phrase. So then we loop back. If the first character does not equal the second character, which is true now, we say done equals true, so done is true. Then we say len equals len minus 1, phrase equals right. So then it would become yx. Then we exit because done is no longer, done is true. So then we go until len is less than 1, which is false. So we come back here and we say done equals false again. Writing over the code, but that's okay. New phrase equals new phrase plus the first character of phrase. So it's y. So it'd be d, y. We repeat, if first character does not equal the second character, then done equals false. Done equals true, so true, because y does not equal x. Len equals len minus 1. Phrase equals right. So just be x. Then done equals true is true. If len is less than 1, so is 1 less than 1, that is false. So then we say done equals false. New phrase equals blah, blah, blah. So it'd be dyx. Then we say first character does not equal second character. Okay, so one problem is this might cause a runtime error because there is no second character anymore. It's just x. So that might cause a runtime error and cause the program to halt. So I think that's what they're talking about. So that's what I suspect. So yeah, so that's probably what is going on. Because len has to be less than 1, so that doesn't, yeah, that's probably the error then. That's probably what you would be concerned about. So I'm just checking my notes here. So yes, anyway. Yeah, so that's the problem. Okay. That's how you do it. So that's how a desk check. There's nothing really kind of you need to worry about beyond that. You just have to like as I said, just map out all the variables and then just go line by line and just draw everything out. And then if there is an output, you draw it, right? But in this case, it's just a runtime error because there's no second one. So correct any logic errors in the algorithm. Okay, so this isn't a logic error. This is like a runtime error, but basically like fix the problem. So the problem is that this obviously we identified, this has to be less than or equal to 1. So you avoid the scenario where you're trying to look at the second character, which doesn't exist because you removed it. So that you just have to basically say that and you'll get all the marks, right? This is like the easiest 3 marks of your life, right? Like most of the work's done in the desk check because if you see it, then you do it. Now, the other thing I'll say is with these algorithm problems that are kind of a bit harder, they usually give you the like breadcrumbs that you need to solve it. So in this case, they just said, try this output, right? Try this string. And that's basically like the gold that lets you win. Like I didn't even fully like look at what these inputs are. Like I just ignore them. So use an example, explain why programmers need to use the different data types in their code. okay, so this is the question of data types. So for example, so the reason we have data types from a fundamental perspective is literally one, it's to basically be space efficient. So for example, if you only need to store a number, like a whole number, you only need an integer, right? Which, you know, an integer can be 2 to 4 bytes, right? So a byte is 8 bits, right? So 1 byte equals 1 bit, equals 8 bits. And a bit is just a zero or a 1. So an integer can be 2 to 4 bytes, or you might hear it as 16 to 32 bits. Now, you know, for example, if you just need to store a number, right? If you compare that to, say, a character, right? So a character can be a bunch of different things. You know, it's like 0 to 9, A to Z, lowercase, A to Z, uppercase, and then a bunch of like weird characters like exclamation point and ampersand and all that, right? And so a character, you know, could be like, say, 6 bytes, right? Or actually, no, not even 6 bytes, sorry. It could be like 8 bytes, right? In the case of the UTF-8 character system, right? So, you know, so almost like you can half or quarter the size, right? But data type allows you to be super efficient with how you allocate memory in the computer, right? So I would say an example would be like, oh, if I need to store a number, I would store an integer, not a character, right? So that would probably be enough if you just explain that. That would be enough to win you the marks. The other thing you could do is literally just say like, the other reason is to is kind of like validation. So it's like if you have an integer, you can start doing mathematical operations on it. So like plus, minus, subtract, divide. Whereas with a string, you can't do any mathematical operations on it. So if you're doing any mathematical calculations, you can't do it on a string. So unless you convert it later, which defeats the purpose. So, moving on. Results of an array containing 200 records. The following table shows a sample of the array contents. Write an algorithm that displays the highest score and names all the people who have that score. Display the second highest score and names all the people who have that score. Okay, so the is an array, not a record. It's an array. So it's very strange that they said it's an array and not a oh, it's an array containing 200 records. My mistake. So it is a record. It's just an array of records. Okay, so so write an algorithm that displays the high score and names of all the people who have that score. Okay, so in this case, they say you have this array, but they don't tell you how they give it to you. So in this case, you can just say, we'll just say highest score, right? We're going to call our algorithm highest score. And I'm going to, instead of saying get input, I'm just going to feed the array as a parameter or argument. Now, if you might be wondering what is a parameter or an argument, the idea is that programming, we have this idea of the modular approach where you have the main module and then you have submodules. And in order to avoid cross-contamination of data between modules, you have this kind of kind of like a doorway between modules, right? So you pass only the data that you want to pass between the modules. So in this, what we call those arguments, right? So this doorway or bridge between the modules, which is what we call the parameter, serves two purposes. One is to avoid cross-contamination. The other is just to create a black box environment where like I don't care about how you process this data. I just expect this output. So this allows you to organize your code in a bit of a better way. So results is an array. So I'm just going to call, actually, what I might do is I'm not going to call the array. I'm just going to call it results. So you just literally say begin, highest score, and then you put in results, right? So just so you know. I think what would also be fine is if you said input results, right? Right. But I prefer this way because it's probably a bit better. Okay, so we want to display the highest score. So okay, so the data doesn't look sorted, so it's unsorted data. So in this case, the fastest way is just to do a linear search. So I would just simply use a for loop. So you can just go, the first off, we'd say, and then okay, so we might have to do multiple, like in sake of speed, we'll just say highest score equals, we'll just say equals 0, and second score equals 0. So then basically we need to navigate the array. So whenever you have an array you want to navigate it, you have to use a loop. So you say for, we'll just say for I equals 0 to 200 inclusive because there's 200 elements. Or I say I equals 1, oh, starting at index 0. So for I equals 1 to 200, we don't have to write step or anything because we're incrementing by 1. Now we're going to say if results 1 dot score is greater than highest score, then I'm going to say highest score equals results. Actually, okay, so just to save us a bunch of time, we'll just say score equals results I dot score. Now notice how with a record, how you access it is almost like you access it like as if you treat it as an object. So basically like you have the array results, which you access normally, and then use the dot to then access a field in the array. So it's the same kind of syntax of an object, but yeah. So so then you say if score is greater than higher score, right? Then highest score equals score. And then you have a second if statement that says if score is less than highest score and score is greater than second score, then I'm gonna run out of space here, so I'm just going to pop it over here. If score is less than high score and score is greater than second score, then second score equals score. Yep. And if and 4. All right, so that should pretty much do it. So if the score is less than the highest score, but greater than the second score, then that's the second score. So I think that logic makes sense. And then basically once you know the highest and the second score, you can create a second loop. So say for I equals 1 to 200 and say score equals results I dot score. And the reason we need a second loop is because we need to establish what is the highest score first, and then basically you navigate the entire array again to find, so then you say if score equals highest score, then basically it's like a repeat. So then you say display results I dot name and if, and then you basically do the same, score equals second score, then display results I dot name. Okay, and if next I. Okay, so basically you need those two loops. So you need the first for loop to establish the highest score, and then the second highest score, and then you have another for loop which basically prints out anyone who matches those scores. Right. So in this case, let's say the highest score was 45 and the second highest was, I don't know, 23. You'd set the highest score to 45. And then the second score would be 23, and then you print it out. So that would do it. So as I said, you don't have to use a for loop. You can use a while loop if you want. It's totally fine. So that would solve the equation. Contrast the purpose of the program counter and that the accumulator. Okay, so once again, fetch execute cycle. I could literally talk about the fetch execute cycle for an hour. And this course is kind of nasty in that it will give you, it'll like do like a 2-marker, like the entire exam and like that entire topic of fetch execute cycle, and they'll only give you a short thing like this for 2 marks, right? But it's one of the harder parts of this course is understanding it. And, it's kind of it's like it's a real shot in the dark whether you actually have to get a big question on it. So in this case, it's giving you this. So the simplified explanation would be program count, like literally to answer this question, define the terms and then just have an extra sentence explaining the contrast, right? So you just say the program counter stores the address of the next machine code instruction to be executed, okay? And the accumulator stores the result of a calculation in the arithmetic logic unit, right? So those are the literal definitions, right? So the arithmetic logic unit is part of the central processing unit, the CPU, and it's reserved for doing all the math operations, right? Which essentially is addition, subtraction, multiplication, and division, right? So whenever you do a calculation, like say A plus B, the result would be stored in the accumulator, right? So program counter and the accumulator are also called special registers, right? Because they have a special function, right? Whereas a general register just stores generic data, whatever you want. Special register is reserved for these specific operations. So literally, if you even if you wrote down half of that, they'd probably give you the marks, right? So, but the fetch execute cycle is very involved, and almost like 95% of students will get it wrong, right? Or even more, like 99% of students will not get it right because it requires I had one student who I literally had to grill like for like hours, for like weeks, and just kept testing them over and over again. It's a very difficult thing to pick up. So anyway, moving on. So here we go. Assembly instructions for the CPU. Once again, another really tough topic that you know, only worth 3 marks, but whatever. Okay. Yeah, instructions. Assembly code. Okay, so by the way, one thing you should note is there's high-level languages, there's assembly, and then there's machine code. So don't get this confused. Assembly, like what you see here, is not machine code. Machine code is the zeros and ones. Assembly are these like instructions that you see. And the high-level language is like Python or like JavaScript or whatever, right? Or C. So, all right, consider the following code fragment. Assume that the variables A, B, C, D initially contain the values 6, 4, 1, 1. This fragment, blah, blah, so perform a desk check. All right. Okay, so parameter code is loaded in the CPU at address 2000, just decimal numbers. Each decimal numbers, interesting. Each instruction is 4 bytes long. For desk check, to the following code fragment. Yeah, loads, stores. Okay, so basically, given the data, execute the assembly. Okay, so load A. So load the contents into the accumulator. So we can just say, I might just, so load A. So that means 6 goes here. So I might just 6. So sub TRB. I'm just going to cross-reference it. So sub TRB. Subtract the contents of Y. Okay, so basically it's accumulator minus Y. So whatever's B. So it's basically going to be 6 minus 4, because B is 4. So it's going to be 2 now. Jumping to load label 2. So basically it means jump. So jump. So load D. Load the contents of B into the accumulator. So it's going to be 1 now. So jump in, just jump means jump to the label, subtract C. Oh, so this would be the program counter as well, would be 3. So the one thing with the program counter is you don't want to say 20001, you want to say 20004, because each instruction is 4 bytes long. All right. So you want to say 2004, and then you also, so we do 1, 2, 3. Two, 0, 0, 8. So I think to be technically correct, we want to say the 1 skips 1, because that's a jump in, that's the jump. So we write the 1 there. So that would be 2004, 8, 16, 32. Oh, fuck. It would be so 0, 4, 8, 4, 16, 20, 24, 28, 32. So 2, 0, 3, 2 goes there. because that would be, so that label 2 is at 2032. Subtract C. So 1 minus 1 is 0. So now we're at 2036. And then output, display the value in the accumulator. So it'd be 0. And that would be 2, 0, 4, 0. And nothing gets changed in here. So I think that's it. I think that's all you need to do. Just double check here. Wait, what is jump? Ah, my mistake. I thought jump was the same, but it's not. It's jump n, which means only jump if the thing is negative. So we need to go back here. So I made a mistake. So only jump if value in the accumulator is negative. So what we've got to do is not jump. So we're here now. So we don't do anything. So then we store A. So store is what store? Store the contents in the accumulator in Y. Okay, so we basically store the 2. So at line 2012, we store the number 2 into A. Okay, then we load D into the accumulator. So that's 1 goes there, so that'd be 216. Then we add C. So what does add do? Add the contents of Y to the accumulator. So add C. So C is 1. So it becomes 2. So 2020 now. And then store in D, store whatever's in there in D, and then jump to label 1. Store whatever's in there into D. So D, so 2, 0, 2, 4, so 2 gets stored into D. Then jump back to label 1. So then we have 2, 0, 2, 8, and you jump. I don't think you need to write the jump, but so I'm not going to write everything out because you kind of know the process, but you basically jump to label 1, and then you would load A again. So A was 2. And you subtract B. B is 4. So the accumulator, so you'd load A into the accumulator, which at that stage is 2. Then you minus the B. So the accumulator would be minus 2. And then you jump N to label 2. So then you'd load D, which is 2. Subtract C. So then you basically output 1. The output of the algorithm would be 1. So yeah, sneaky. So be careful. I took a shortcut, which was a mistake. Always be careful with the jump. So always cross-reference to the actual instruction. So there's 2 jumps, jump N and jump. So just be careful. Okay, so that is that is section 2. So I might leave that there and then do another video for section 3, because section 3 is split into 2 parts. So see you in the next video.